Good morning, everyone, or good afternoon, depending on where you're attending this webinar from. First and foremost, I would like to thank you all for taking time out from your schedules to attend this webinar. Welcome again. Today's topic, ASE61850 SCL Manager, comparing top-down and bottom-up engineering approaches for 61850 substations. IEC61850 engineering process recommends and illustrates a top-down flow starting with a substation specification or a SSD file. However, practical implementations on the ground in pilots as well as live substations sometimes employ a bottom-up approach. This webinar illustrates how these two different approaches work and the salient similarities and differences between them using a proven third-party SCT tool. A brief on Kalkitech. Kalkitech has long been an advocate of open standards and standards-based communication to facilitate interoperability in the true sense. Our products and solutions enable customers implement mission-critical applications across the smart grid solution spectrum, ranging from substation automation to wide area monitoring, distribution automation to advanced metering infrastructure. To introduce myself, I'm Gautam, and I take care of Europe and Latin America business for Kalkitech ASE offerings. ASE being the US-based company acquired by Kalkitech in 2014-15. A few points to keep in mind before we start off. Since we have a large number of participants, this is a listen-only webinar. However, to facilitate clearing of your doubts or queries that may arise during the course of the webinar, you can kindly send us your questions by typing in the window provided during the talk itself. We would try to address most of your queries here or come back to you individually in case we run out of time. The presented talk would be for 40 to 45 minutes, followed by questions selected at random. I would now like to introduce you to a panelist for today's webinar, my colleague, Mr. Vinu Warrior, Vice President and Principal Engineer, ASE Tools. Vinu serves as a Group Head for Kalkitech ASE Product Development Group. In his role, he oversees the activities of product development for a suite of products related to protocol devices, tools, and protocol test sets. He has more than 19 years of industry experience designing and implementing communication solutions in the energy industry, specifically in the areas of power system control, communication, and automation. His core areas of interest and expertise are design, analysis, and implementation of communication protocols in the energy automation industry, participation in international standards bodies related to these communication protocol standards, as well as training and extensive consulting engagements around the world. In addition to extensive worldwide training and consulting engagements, Vinu with his team has successfully participated and showcased our vendor-independent tool, the ASE61850 SCL Manager, at various multi-vendor interoperability events like the IOP events in Brussels in 2015 and New Orleans in 2017, where the feedback on our tool has been very good. Without any further ado, I would now pass controls to Vinu, who would take it forward from here. Over to you, Vinu.
All right. Thank you very much for that introduction, Gautam, and good afternoon, or I see a lot of good mornings also here to our participants. Thank you very much for joining. We'll start right away with the session. So today's session is about the substation configuration language, or using SCL for IEC61850 substation configuration. But more specifically, we will be discussing some terminology that has arisen in recent terms, that has emerged recently regarding SCL configuration, specifically the terminology related to top-down and bottom-up engineering. So there seems to be a lot of opinions floating about what these are and what they mean. And I thought this would be a great opportunity to share our view or our take on this subject. This is the agenda for today. So we'll have a very quick one slide introduction to SCL. What is it? I'm not going to spend a lot of time on this, as I wanted to explain before. The main focus of our discussion is going to be on the top-down and bottom-up engineering processes. So we'll cover this with a few illustrations, and this would also be a good time to introduce the different SCL file types. As you may be aware, the list of types has been growing a little bit, and it continues to grow. For example, in the recent period, we now have a concept of an ISD file, an IED specification description. So we will probably spend some time to understand why that is coming out. We'll then flesh out all these illustrations with a demonstration using our ASE61850 suite tool, the SCL Manager. We'll start with the classical top-down flow. We'll create an SSD, we'll specify the logical functions. Then we'll move on to import ICDs to meet those specification requirements, and we'll map the functions from the spec to the devices. And at this stage, I would like to focus on some limitations of the current SSD process and the workaround that emerged to deal with it. This is where the ISD file discussion would come up, the one that we just mentioned a minute ago. We'll continue with the top-down flow. We'll configure datasets, reports, GUIs, and build a full SCD. It's going to be a limited demo with just one feeder and a few elements for the sake of the webinar, but it will still take you all the way through the flow. And at this stage, I would like to bring some exposure to some sections that do not usually get much traction, that usually do not see much coverage in talks like this. I want to spend some time on the IED services, for example. I want to cover the IED service declarations in the ICDs and how the SCT has to respect those constraints that are imposed by the ICT. We could also, at the end of this process, export a CID from the SCT as a final step. It doesn't really provide much value, but we can do that if we have time. And then we'll discuss the bottom-up flow, and we'll examine the main differences when compared with the top-down approach. Finally, we'll try to conclude on whether these two things are really as different as they claim to be or as they are understood to be. After our conclusions, we'll have some time left for questions and answers. And that's the agenda for this session. And I hope this will be an hour well spent for all of you with the content that we have planned for this session. As I promised, a quick one slide introduction to what is SCL. Well, SCL is a language. It is used to define configuration information of substation IEDs and client devices. So it is used to convey or carry configuration information between tools. Just like the IEC61850 protocol is used to convey or carry operational information, control data, or parameters between different IEDs and clients. In the same way, this language is used to carry configuration information, and that is between tools. There are three kinds of tools that we will discuss. They are the IED configuration tools provided by the IED manufacturers. There are system configuration tools where you have the possibility now of independent third-party system configuration tools like ours, the one that we use in the demo, as well as vendor-provided SCTs. And finally, the third tool is the system specification tool. So data exchange in this process is carried out in the form of exchanging files written in SCL. That is, it's basically an offline process. It's not like a client-server request response kind of a process. And finally, the interoperability of SCL when it goes between these tools is a totally different thing as compared to the interoperability of the 61850 bus communications that go between the IEDs and the clients. Now we'll get into our illustrations. This is a view of a typical 61850 station bus. You'd expect to see IEDs like protection relays, bay controller units, reclosers, fault recorders, and a lot of other stuff connected to an Ethernet switch, which is what you call the station bus. And typically you would also have a client machine, which could be a station HMI, or it could be a gateway. So it could be a protocol converter or gateway that translates the 61850 statuses, reports, and control commands. It translates those to a SCADA RTU protocol, like DNP3 or IEC104, depending upon your geography and your preference in protocols. You could also have both station HMI as well as a gateway to a NCC. The comms on this bus are mainly the IED to IED goose and SV traffic, as well as the client IED traffic of reports, reads, controls, etc. Now, when it comes to top-down engineering, the IED configuration tools come into play here. These are tools that are provided by the IED vendors, and they incorporate proprietary technology. The other tools involved in this process are the centralized system configuration tool, that is the SCT, as well as a system specification tool, that is the SST. Now, the top-down approach starts with the generation of a specification by the SST role or the SST tool. The specification is generated as an SSD file, and this SSD file is imported by the SCT. So at this stage, the system configurator user, the user of the SCT tool, has a clear picture of the requirements of the system, and he either generates or he solicits IED ICD files. Let me just set up my pointer here. Okay, so he solicits IED ICD files from the ICTs, the IED configuration tools of the selected or the participating IED models. Nowadays, in the times of these multifunction devices and highly configurable devices, this stage typically involves some amount of pre-configuration of these IEDs, which could involve changes in its data model or changes in its services to fit the envisaged role. The SCT user has a picture of what IED fits what role in the specification, or what IED can be made to fit what role in the specification by making small changes at the local level. So the user now imports the ICD files that are generated by the ICT files into the SCT, and he then performs the core configuration of the system. That is, basically he has to name the IEDs, give it a context, assign network addresses, map the functions from the specification, the single line diagram in the SSD file to the IED, create data sets to set up the communications, create reports, report control blocks, goose control blocks, and he has to map the signals between the IEDs, IED to IED signal mapping in the case of goose, or from the IED to client for reports. The finished product is an SCD file that can be used as an input to the ICTs, where the ICTs will use an extract from the SCD file to program their respective IEDs, and it can also be used, the SCD can also be used to program the client HMI or the gateway. So, salient characteristics of top-down engineering are: 1, the usage of a standard specification; 2, ICDs being used as templates containing the IED capabilities and brought into the SCT, where all the engineering is actually performed in the SCT; and 3, the output of the SCT is piped back to the ICTs, and that is what actually ends up configuring the IEDs. As you see here, all these points are contradicted in the bottom-up approach. The bottom-up approach also starts with a specification, except that typically it is the traditional specification that is used now in the form of office documents. It's got tables and figures and clauses and information. So it is still used by the SI role, the system integrator role, but it's not really used by the SCT. Please note the direction of the arrow that I'm showing here. So it is something, it is information for the system configurator user, but it's not information that can be processed by the SCT, because the SCT only understands files written in the substation configuration language. My mouse is misbehaving. Hold on a second. All right. So the bottom-up approach, the next step in the bottom-up approach is to go and perform some of the pre-configuration that we talked about, except that in the bottom-up approach, the pre-configuration is actually the entire configuration of the system. So the user knows what the requirement is, and he will perform all the configuration of the IEDs using the ICT. Knowing the requirements, the user can create the data sets, create the reports, create the goose control blocks, assign names, IP addresses, and perform all the configuration of these IEDs using the ICTs. So this is where the difference number 2 comes into the picture. The first difference was the fact that we don't use a standard SSD file for the specification. The second difference is the engineering. Most of the engineering is done at the ICT level and not at the SCT level. Finally, as a form of paying lip service to the standard, the user will export an IID file from the ICT tools, which is basically an instantiated IED description. Now, an IID file is different from an ICD file in the sense that it contains not just a template of the functionality that is available, but it contains all the engineering that has already gone into the device. That is, it contains the data sets, the reports, the GUIs, the addressing information, everything that has gone into the configuration is available in this instance, IED instance, instantiated IED description file. Now this file is imported into the SCT, where the SCT can merge that information. It can resolve all the information there and generate a SCD file. Now the difference here is that this SCD file that is generated is not really needed. It's not necessary to take this back to the ICTs to configure the devices because that is already done. But the SCD can still act as a global view of the configuration of the system, and this is something that can be archived and used later when there is a modification to the substation which requires re-engineering. And at that point of time, it could use the top-down approach. There is no particular reason to avoid using that. The SCD can still be used to configure the client or the gateway. It looks like I cannot break out of my mouse roll here. Okay. So this is, let's take another look at another view of the top-down and bottom-up process along with all the file types. The top-down flow from the system specification tool comes first, that is the SSD file, which is imported by the system configuration tool. The system configuration tool solicits ICD files, maps the functions from the SSD to the ICD, and performs all the configuration, including signal mapping between IED to IED and IED to the client. And then it exports an SCD file, and the SCD file is used by the IED configuration tool to program the IED. Just one note here is that the CID, the configured IED description information, this is a subset of the SCD, but there's no rule that states that this information, when it is programmed by the ICT to the IED, it does not have to follow the standard. Typically, the information that is extracted from the SCD, which is the CID information, would be merged along with other information, for example, logic, which may be generated by the ICT, and that entire bundle will be programmed to the IED in one step, and that could be a proprietary usage. Now, are these approaches, we just talked about top-down and bottom-up, so are these really mutually exclusive? Do we say that we either follow a top-down approach or a bottom-up approach and that these two cannot coexist together? Well, not really. And are these processes exactly as I described now? And once again, not really. Especially when it comes to bottom-up engineering, that seems to be a highly abused or overused term. There is no very clear definition of what bottom-up engineering means. For example, even the definition of an IID file. An IID file is typically different from an ICD file in the sense that it contains engineering information. But technically speaking, if the IID file has an IED name, that is an actual IED name and not just the word template, technically speaking, you could call that an IID file, even though it doesn't have anything else. Obviously, that's not a very useful IID file. It requires at least the presence of context-specific data sets to be engineered to be present in the file for it to qualify as an IID file. What about reports, report control blocks, goose control blocks? Well, you would find those in ICD files as well. You could find reports and goose control blocks already created, except that typically they would not be mapped to any data sets. And that would be the stage that would be left to the SCT to perform, where it uses those report control blocks by creating data sets that it requires and mapping them to those control blocks. So there is a lot of variation or flux in the concept of what goes into an IID file and what constitutes bottom-up engineering. Very technically speaking, the concept of IID file was not created to satisfy a role where everything is done at the IED configuration tool and imported back to an SCT system configuration tool. The concept of IID was generated as a natural part of the top-down flow, except that it's in the reverse direction. That means in the top-down flow, once you have finished configuring and instantiating all the IEDs in the station, there are many use cases where you may require some local re-engineering of the IED using the IED configuration tool. Now, if you perform a local re-engineering here, and if you try to export an ICD file, you're back to square one. When you import that ICD file here into the existing system configuration, you need to perform all the configuration steps that you had performed earlier, and you need to ensure that you do not deviate from what the rest of the devices were expecting. So obviously, the solution was for the IED configuration tool to export not an ICD but an IID, which contains all the configuration that had been earlier provided by the same SCT, along with the changes that it has made. And now the SCT can import the IID, merge the content, and resolve the few things that are changed. So that is our take on what is now being called as top-down and bottom-up engineering. We'll now quickly go through a demonstration. We'll create a SSD, a specification, system specification description, and we will try to achieve the following objectives. I have an SLD with a simple radial distribution. There is a single incomer connected to multiple outgoing feeders through a bus bar, each feeder in a dedicated bay with its own isolators and breaker. Functions specified are measurements and overcurrent protection, the basic overcurrent protection on the feeders, the incomer as well as the outgoing. And just to keep things interesting, we'll also specify a reverse blocking. So this is an interlock where the start or the fault pickup on an outgoing feeder is used to block the incoming protection, the incomer feeder protection. It prevents the incomer protection from tripping the incomer so that the rest of the outgoing feeders are still serviced. Basically, it increases the selectivity of the fault handling. We'll generate this SSD and then we'll continue with the top-down flow by importing ICDs, mapping and configuring to develop an SCD. So now let me just minimize this. All right. I still don't have my mouse. Okay. Now, all right. You should now be looking at my SCL Manager screen. So I'm not going to spend a lot of time drawing this during this webinar because it's going to take maybe several minutes to do this. So I have a prepared drawing. This is a prepared specification. Now I've created a project called Web Demo, and you can see the SCD that has been generated here, and you can see the tree view if you want a smaller description. So essentially it's a substation with a single voltage level, and in the voltage level we have a bay for the bus bar, a bay for the infeeding feeder, and two outgoing feeders. And I've created a single line diagram which is essentially the same thing. So the voltage level is just the lower voltage level, that is the downstream part of the transformer connected to the bus bar, and the outgoing feeders connected to the bus bar with a breaker and isolators. Now when it comes to specifying the functions, all you need to do, the classical approach to specifying functions in the SSD is to associate L nodes. So what I've done is you can specify the protection function on the bay. Actually, there is no hard and fast rule on where you specify the function. You could specify it on the incoming feeder, or you could specify it on the circuit breaker, or you could specify it as part of the bay. So I already have the overcurrent protection specified. I can go ahead and add the measurements. So I add my L node, I go to my measurements and MMXU. So in this way, I can add my functions. Obviously, the circuit breaker already has the functions mapped. The circuit breaker has the XCBR, the interlock, and the control switch specified. Similarly, we have specifications for the outgoing feeder. Here is already done. Now, this brings us to one of the limitations of the available existing SSD process. I can specify that I want measurements. I can specify that I want overcurrent protection. But is this sufficient? When I say measurements, MMXU, for example, is a logical node that encompasses more than a dozen data objects. There is total active power, there's reactive power, there's phase-to-phase voltages, phase-to-ground voltages, phase-to-ground currents, individual Y and delta currents and voltages. So there are dozens of data objects, and how do I specify exactly what measurements I wanted in my specification? Now this is currently a limitation. For example, the XML that I have here provides these properties. It provides a logical node class, and that's it. I can say MMXU, which is my way of informing the system integrator that I want measurements, but the rest of the properties here are related to the IED to which it is going to get mapped. And the IED to which it gets mapped is not a specification time activity. It is a system configuration time activity where the system configurator will map this logical node to an actual L node belonging to an actual IED that he has imported into the system. And that is at that stage that you will have a real IED, you'll have a prefix instance and a real instance of a logical node, which has a logical node type, which is detailed out in the data type template section of the file, which will give a full view of all the data objects that are available. So at this point of time, I have no way to specify in this detail. So this is where the virtual IED comes in, but we'll get to that later. The other problem I have is I have specified overcurrent protection, but typically I would have multiple instances of overcurrent protection. Now I can add them. That means I can go here and I can add one more. So L node, I go to protection and I add one more. Fine. I've got two PTOCs. So now I can cater to phase faults, phase-to-phase overcurrent faults and phase-to-ground faults. I can do that separately. So be more relevant out here at the outgoing feeder. So I could have multiple PTOCs. But when I have multiple instances of the same logical node, how do I specify the semantics? I don't have a lot of properties here. How do I specify the semantics that one is for one kind of protection element setting and one is for the other one is for a different purpose? This is another limitation that is currently in our SSD process. Let's see, we'll see how we can deal with this later. But right now, let's continue with the top-down flow. The process for continuing the top-down flow is as a system configurator, I import this SSD file. I look at this picture, I look at the requirements, I look at the properties set in the XML and the L nodes, and I now look for IEDs that can serve this purpose. That means I need to go here and add IEDs. Now what I've done here is I have prepared another instance of SCL Manager. So I will need to bring this to my projection. Okay. So I have another instance of SCL Manager running in which I've created a workspace called IED Templates. I use this just to manufacture ICD files. So now this is, you could say that this instance is acting like an ICT. As you may have noticed, the SCL Manager can be used as an SST, system specification tool. It can be used as an SCT, system configuration tool, and it can also be used to create ICDs. So it's like an ICT. Now I created a few IEDs here, a BCU, a relay, and a client. If you look at the BCU, I've added logical nodes, LLN0, XCBR1, the isolators, the two switches, a control switch and an interlock switch. Okay, it's a bare bones ICD, but it will serve the purpose. In the relay, I have logical nodes that will serve my purpose. So I have PTOC1 and 2, PTRC, that's the trip conditioning. So essentially the output of the individual protection elements will be ORed together in a matrix, and PTRC refers to the final output of the protection. And I also have my MMXU1. So if I have exported all of this as ICD files. Essentially, I just click on an IED, I click on export, and I have already prepared them on my desktop. So I've created these ICD files. I'll not do that again. And I just need to import this in the other SCL Manager instance, that is my specification. Okay, this is where I've loaded my SCT. So where is my mouse again? Okay, it's there. All right. So now I add my IEDs. This is a typical use case where when you're using this tool as an SCT, a system configuration tool, you typically import your IEDs as ICD files, which you import from the file system. It's been sent to you by the ICT files. So I say from the file system, I select on my desktop and I select my BCU and say open. I actually need two instances of my Bay controller unit, one for the incoming and one for the outgoing. And when I do this, I have an option to reuse the data type templates. There is no sense in duplicating the same data type templates for two instances of the exact same ICD. You can just have two IED instances which refer to the same data type template. So this helps you reduce the size of your overall SCD. So I generate this. I'll simply give it a name as BCU. And this is another quirk of SCL Manager. I should follow the system configuration mode for the IED, which ensures that SCL Manager is constrained to respect all the rules of the IED without trying to edit things that don't belong here. If I move to IED configuration rule, it gives me free access to modify things as I will, which is not what I want to do here. So I'll set it up in system configuration. I'll take the default for now and finish. So now I have my two IEDs that you can see here, BCU1 and BCU2. If you actually look at the SCL file, which has got updated with these changes, you will find that they are reusing exactly the same. So this is my first IED. This is BCU1. And if you look at any of the logical nodes, you can see XCBR. This is XCBR instance 1. It is using an LN type XCBR1, which is a reference to the data type templates. And if you go to the data type templates, you will see XCBR1 is a defined logical node type. So these are my data type templates. And I have XCBR1 is a defined logical node type, which gives me detailed information about all the data objects in that logical node. It gives me additional information saying that the XCBR has, besides behavior and local, it has got an operation counter, the position, block opening and block closing data objects. And I can further drill down into this because each of these has got a type. These types are the data object types, which I can find elsewhere downstream in this file. And this gives me the detailed information that I was looking for. Now I have my BCUs loaded. How do I map my functions? I just click on the L node that I want to map. I click on link. my data type templates. Next, I'll call them relay. I will go to system configuration. Next, next, and my relays are online. Now I can map my MMXU, and it shows me that I have two devices which have MMXU, and I can go ahead and map this, right? But just to keep things interesting, let's look at what MMXU actually has. Now, if I go to my relay 2, my relay 1, where I mapped the logical node MMXU, and if I look at the type, all right, I'm not allowed to look at it. I'm not allowed to change it. I can only see it because I'm in system configuration mode. This is one of the constraints. I can't just modify this. Now you can see here, this is pretty much an empty MMXU. There are no data objects here. So specifying MMXU and looking for MMXU in a ICD that you select does not really give you much benefit. If you are interested in the total active power, or you have the delta, that is the phase-to-phase voltages, or you have the Y object for the individual phase currents. If you're interested in these measurements, then there should have been some way for you to specify them and not just specify your MMXU name, which is why you ended up with this situation. Now, how would I rectify this? In my normal scenario, I would go back to my ICT. Okay, so this is my ICT. Yes, IED templates, and I would go and modify this here, because here I have full authorization or rights to modify the data model. So I could edit the type. I could go to MMXU1. I could edit the type, and I could add the data objects that I want. But I'm not going to do that. I can just, if I do this, I'll have to export the ICD file and import it back here again. So I'm going to cheat. That means in my SCT, I can switch my IED properties and set the default configuration mode from system to IED, which gives me an override to modify things as I like. Now, this is not really something that I would advise people to do unless you know what you're doing, but I just wanted to illustrate how the same tool can be used in ICT mode as well as in SCT mode. So now that I've done this, I could go to MMXU1 in my relay 1 IED. I could edit the type, and I could set up whatever is the data objects that I want. Okay. So now the type has been modified. All right. So this brings us to one of the solutions for the problem that we mentioned at the specification time, that is the inability to specify detailed functionality. Instead of just specifying MMXU1, one of the workarounds that has emerged over the last few years is that the system specification role or SST would actually create an IED. The IED could be named as a dummy IED, or anything that the customer requires, the utility requires. And the purpose of this IED is just to serve as a placeholder where the utility can specify the detailed data model that they expect, the detailed data objects, the services, which also gives the utility the option to actually perform engineering with these virtual IEDs. You can actually engineer the reports, the data sets, you can engineer the signal mappings, and give the whole thing to a system integrator. But the system integrator's job would then be to replace those virtual IEDs with real IEDs. And that is a concept that is now being called as the IED specification description file. That means if you created a dummy IED like this, you could actually export this information, and the file that you get with all the configuration information is essentially an IED specification description. It is not an ICD, it is not a CID, it is an ISD. Okay, so that is one of the workarounds that I wanted to highlight here. Now, the rest of the configuration process in top-down is very straightforward. I have my relay. I go ahead and create my data sets. The first step is to create data sets. So I create my data set inside LLN0, and I call it, let's go to relay 2. That means I want to, the main purpose of the specification that I had was to map the start protection PTOC start or pickup of the fault to send it up to the incoming feeder. So let me go to this. I take PTRC, go to my data sets, add a data set in LLN0, and I say PTOC start in my outgoing feeder data set. So select my data. Now the data I want is my PTRC. I'm sorry, my data model is not complete. So what I can do is I can pick my PTOC1 and pick my start, general, direction, quality, and the time. Or I could have just picked the data object and mapped it here, but in any case it's done. So this is my data set, and I'll go ahead and create my goose. So I add a goose, and I call this my outgoing feeder start goose. I'm supposed to provide a system-wide unique name here, so I use the same one here, and I map my data set. And I have my settings here. I could make this a routable goose, or I could make it a fixed offset goose. I could specify security if it was available, and I could perform my mapping of the IED name to which is subscribed, but I won't do that right now. I'll just go ahead and add this. So in the same way, I can create a report and map it to my client. So I can create a report, add a report. I'll place that also inside LLN0, and I'll call it my outgoing feeder start report. Once again, I need a unique name for my report ID. I use this here, map my data set, and I have all my settings here. Make it a buffered control block or unbuffered report control block, my integrity, period, my trigger options, option fields, and the client ID to which I want to map this. So I'll just add this for now. Now the rest of the top-down flow is to map these signals. That means if I start with my goose, I need to map my general. Let's say okay. Now I want to map this to my incoming feeder relay. I select the destination logical node, and let's say I map it to PTRC. So I'll use this here as a blocking signal to ensure that the trip on my incoming feeder does not work. Now I have the option to add this as a new external reference as an input, or use a predefined input. So I'll just go ahead and use external input. Now here we come across the first aspect of the IED services. I wanted to spend some time on this, so I have essentially left the settings at the default. Now here SCL Manager wants me that the destination service setting does not allow me to map inputs to the selected destination IED. That means in the client services for the destination IED, I need the maximum number of goose to be at least 1 so that I can map this goose. But right now it is not. So this is a problem. So I say, okay, I cancel this step. Now if I go to my destination IED, that is relay 1, and I look at the IED services, you can see the first set of services are the client services. The client services in IED services refer to what support this IED serve has when acting as a client for goose. Now it says goose is acceptable. The client service is already set to accept subscription to goose, but unfortunately the maximum number of attributes and the maximum number of goose are still set at 0. So this is how the IED services impose constraints on the SAT2. Now normally I would have this rectified by the ICT, but in my case relay 1, I think I have already set it to IED configuration mode, so I'll cheat. I'll use a shortcut. I will close and reopen relay 1, and now under the new IED mode, when I go to my services available, I now have the options to modify these services. This is not something you get in the SCT role. This is something you get only when you are modifying the ICD file. So now I can go ahead and change this. So the first change I will make is I will allow up to 10 goose to be subscribed and say save. Now this is not really going to help me, as I'll just demonstrate. So I'll go back to my web demo, relay 2. I'll try to map this again. Okay, I'll map my general signal. I'll say okay. I'll select relay 1, protection, PTOC1. Now I run up against my second roadblock. Now SCL Manager is telling me that the destination service setting maximum. Oh, I think I did not save that. Hold on a second. So I change this to 10. Save. Map it all over again. Mapping to the wrong device. Oh, I'm sorry. I believe it is overflowing to the second property.
Needs to change the
setting below. I made, there are some more IED services. That's right. Hold on. We'll go to relay 1. I need to set up my attributes so that I can map a few signals. That is true. And the number of goose. Oh yeah. Sorry. This is the one. So I made a mistake. This is the attribute that I should have changed, the maximum number of goose. But instead of this, I was changing the maximum number of reports. So, shit happens during these demonstrations. All right. So now I have this set correctly. This is the limitation that it was correctly pointing out to me. Save. All right. So now this should work. It sort of lost me my punchline because I wanted to go to the next problem in the next step, but now I ended up solving both the problems right away. So now if I map to a destination LN, it allowed me to do that. In the original flow that I planned for this demonstration, I would have run up against my second roadblock, which was that even after adding scope or capability for the destination device to accept number of goose, I would have set this number of attributes as a client to 0, which would have still prevented me from mapping, because to map a signal to this device, I should be able to subscribe to a goose that is controlled by this, and then I need to be able to insert an attribute external reference, which is controlled by this. So the point that I was trying to make was you need to be very careful with the IED service settings. And I wanted to cover some more of these service settings. So these are all the client services where this relay 1 acting as a client, whether it's able to subscribe to goose, yes, to GSSC, no, to reports, no, to read logs, no, the support logical device name. This is an interesting service. Basically, nowadays IEDs have the ability, they expose the ability to be named with a user specific LD name. So originally, when you refer to any data, you refer to the LD name as a combination of the IED name concatenated with the logical device instance property, which is also a string. So you add them together, that is the LD name. But now devices can support a configurable LD name, which is available as a server setting. Let me see if I can find it here. Conf logical node. Yeah, here it is. Configurable logical device name. Now, if I set this as true, this means that relay 1 allows you to set your own logical device name, with which you can override the default name but the same configurable logical device name appears in the client services as a supports logical device name. What this means is, if I support this and the other one is false, it means that my IED does not allow you to change its logical device. It does not support fixed offset goose. It does not support layer 2 goose sending, and layer 3 is the routable goose. So these are the different IED services. Unfortunately, I don't think we have time to go in detail. So with this, we have performed the mapping of the signal. How does this affect? If you go to the SCD file, the XML file that is being modified in the background, and just search for input, you should find an input. Yes. So you can see here that in the destination logical node, we now have an input section with an external reference. And this external reference is now the edition 2 style reference, where you have all this information, the IED name relay 2, the LD instance is protection, the PTOC1, and the DO name is start, and the data name, attribute name is general. There was no internal address specified because this is not yet gone back to the ICT. Additionally, the edition 2 introduces the service type, where the signal is being shared as a goose, and the source, the SRC, which is the source control block name and the source LD instance. This gives you the path to the control block, the goose control block, which is delivering this particular signal to this IED. So this was an essential requirement that came in edition 2, because now you know which goose to subscribe to. In edition 1, you knew what data was arriving in the goose, but you don't know which goose control block was publishing it. So now with the introduction of these, it becomes much easier to perform the signal mapping. So that is one input. We can similarly perform from relay 2, we could map the report. The report data you could map the signal to. In this case, I have not yet added my client, so there is no device that I can use here. So I should have added my client. Import from file system, browse, client. I just need a single instance of this. And now I can go back, map my report, select the signal, map my client. I believe that's not complete because I have not created the logical node list for this client, in which case I could have simply mapped this and it would have arrived as a input signal in the client. So we'll skip that step. So we have gone through the top-down approach. Now let's get back to our presentation and examine whether the bottom-up approach is really anything different. So start from here. I hope it appears on the correct monitor. Okay. So in the demonstration, in the planned script for this demo, the two limitations that I wanted to highlight was, one, the inability to specify fine-grained data in the required logical node. The MMXU example was put there intentionally to cover this example. So as you saw, that is a limitation in the sense you cannot specify the data objects in MMXU. The other inability was the inability to set context to multiple instances of the same LN type, which is used with different semantics. For example, PTOC instances used for different fault types with different settings. You really have no way to provide those semantics. The workaround for the first issue is create a virtual IED in the SSD with detailed data model as required, and if necessary, go ahead and perform the design as well. I mean, you can actually, in the requirement, you could even provide detailed data sets, reports, and signal mappings between IEDs. If you have created virtual IEDs or dummy IEDs or ISDs, that's the formal term that is appearing. It's not yet standardized, but once it does, you can use those. In which case, you could do a lot of pre-design or recommended design in the specification itself. The workaround for the second issue, the inability to set context to multiple instances, are functions and subfunctions. So what are we doing for time? Yeah, just 5 minutes.
5 minutes more.
All right. So I'll just go through this very quickly. In edition 1, the function was something that belonged in the substation, and the function was something that was a part of the substation, and it could have subfunctions, and the subfunctions could contain power equipment. Just like substation contains voltage level, contains bay, contains equipment, you could have a parallel path of equipment being related to subfunctions under functions or directly to functions under the substation. In addition to, it has been expanded a little bit more, that you can have functions and subfunctions, the voltage level and the bay as well. You can see the new arrows that have been added here, which gives us a little more flexibility in adding functions and subfunctions. How do you use this? This is an example taken from a paper on Packworld. You can see this example here. This is a model of a substation. Look at the table on the right. A substation containing a voltage level, containing a bay. Normally, you would say the bay contains conducting equipment, which is the feeder and the circuit breaker, and the conducting equipment has L nodes associated with it, which is what we demonstrated today. But there is nothing that prevents us from adding functions as the first level element, functions in the bay, for example, overcurrent protection, and within that, the L node, that is PTRC, for the overall overcurrent protection of the device, and subfunctions for the different kinds. For example, here, face-to-face faults and ground faults. The overcurrent protection for face-to-face faults can be a subfunction with its own specific set of logical nodes. So here you have PIOC, PTOC, and P direction, which is specified as instances for the phase fault subfunction of the overcurrent protection function. And you have the same logical node types, PIOC, PTOC, PDI, are different instances specified for the ground fault subfunction of the function. So this is one way to provide a more context to the system. Sadly, these names of these functions and subfunctions are not really standardized. So as of now, this is not entirely useful, but it still is a step in the right direction. Now we'll dispense with the last couple of slides. It just tells you how people typically detect what are the types of files by looking at what it contains typically. But as you may have understood now, there are no hard and fast rules. Nothing prevents you from adding in an SSD a virtual IED, in which case, in addition to the header and the substation that you expect, typically you'd find everything else as part of the specification. So we can no longer rely on the old rules for this. This is the final summary. I'll leave it on screen for you to read it. This is just what we covered in this thing. And I think we'll quickly try to move on to questions. Let me just take a look at the questions here.
So, Vinu, thanks firstly for the detailed and informative talk and demo. It was really engaging, and we got feedback from a lot of participants that during the demo we were changing maximum number of reports and notebooks. So that shows that the participants was very engaged, and that helped a lot. Thanks.
All right, so we have a question regarding the importing signal lists into the tool. So we have a way to import, export the IO list that is configured in the tool as of now, but we do not exactly have a way where we can take in templatized or freeform information about signal lists and associate that with the device. So the question I think was, can we just pull in the IO list for a device into the tool. No, you would need to have the data associated with the IED. In this case, I think you're talking about the HMI device. Maybe I can explain this in more detail offline with a direct response to you. That is the first question. Can we go with the...
Yeah, the second question is bottom-up engineering discouraged?
Okay.
Doesn't using an IED export make it a standard process?
Absolutely. So the whole purpose of this today's session was to explain that bottom-up engineering is not really a mutually exclusive style of engineering, though some people did take it that way initially. So it's not that you either do top-down or you do bottom-up, and that bottom-up is related to the older form of engineering. No, top-down is a good direction to follow, and fixed offset. Fixed offset is a support, a service support that you declare, basically to understand if the goose allows you to encode the data in a slightly more efficient manner. That is, for example, in the typical encoding of goose, integer value, the 32-bit integer value like the state change number or the sequence number is encoded differently based upon the value. To send a value of 0 or 1, it does not use 4 bytes or it does not use 32 bits, it just uses 1 byte. But to send a bigger value, it uses 2 bytes or 3 bytes or 4 bytes. So the length is variable, which optimizes the bandwidth but makes it difficult to process automatically. So now fixed offset forces all the data to a fixed offset. So all 32-bit integers will be encoded in 5 bytes, which makes it easy for like automated systems like a programmable logic to extract the data without worrying about how long it really is.
Okay, thank you very much, Venu. Thank you to all the participants also for taking time out to attend this webinar. If you have any additional questions or queries, feel free to drop us an email at marketing@kalkitech.com. We will also be sending the recording of this webinar shortly to all the participants. Have a great day and thank you for attending. Bye. Thank you. Bye-bye.
Thank you very much.